up to this point, I have to mention a few very important results on the limit of 6 types of sequence. The first type of sequence is the sequence of Ln over n when n goes to infinity. This result has been shown in example 7, right? So here we have shown that the limit of Ln over n is 0 when n goes to infinity by making use of theorem 4. There are other 5 very important results. That is, if you have n raised to the power of 1 over n, and you take n goes to the infinity, then what you will get is a number of 1. So this is another important result that you have to remember. You can actually prove the second item in theorem 5 using theorem 4 as well. I'm looking at item 2 in theorem 5, where we are talking about the limit of n raised to the power of 1 over n. This is the same as the nth root of n. So this and this both are different way of writing the nth root of n. To calculate this one, first we have to find a function of fx such that f at n is equals to a of n. Here, the a of n is the sequence in the term, is the terms in the sequence, which is n raised to the power of 1 over n. So it is obviously easy to write down the expression of the function fx, where you just simply replace the expression of n in the sequence by x. So you just write down x raised to the power of 1 over x. So I am now looking at this function. What I'm going to do is that I am going to find out what is the limit of the function fx when x goes to infinity. According to theorem 4, the limit of this fxl would then infer that the limit of the sequence an would be l if because fn is mapping to the sequence of an term by term for n. I think in this case equals or larger than 1. So now let us see how you can calculate the limit of the function of fx. So I'm going to call y as x raised to the power of x. So x power of x is just expression of my function. So I'm going to use the same trick. In order to calculate the limit of y when x goes to infinity, I'm going to take the log of y on both sides. So when I take the log of both sides, I have x and I have then 1 over x as well. So then after I've taken the log on both sides, I'm going to take the limit later. So once I've done that, then I'm going to find out what is the limit of y, ln y, when x goes to infinity. The limit of ln y when x goes to infinity is the same as the limit of x goes to infinity for ln x over x. And here, ln x will goes to infinity when x goes to infinity. This will also go to infinity when x goes to infinity. So we apply the L'Hopital rule. We have actually seen this in the previous example. So finally, when you apply the L'Hopital rules, what you get will be just 0. So in other words, the limit of ln y when x goes to infinity is 0. So what you do is you take the exponents on both sides of the equations. So when you do that, then what you get is the limit of x goes to infinity and exponents apply on y. That is equals to 0 as well. So this will give you the values of y. The exponents acting on ln of y will give you y. So I have just come to the conclusion that the, okay, sorry, I think right hand side is not quite true. So the right hand side is 0. When I take the exponents on the left, I also have to take the exponents on the right. So on the right hand side, it should be the exponents of e raised to the power of 0. E to the power of 0 is the values of 1. Therefore, I come to the conclusion that the limit of x raised to the power of x, when x goes to infinity, is just equals to 1. And this would infer, by the virtue of theorem 4, n raised to the power of n would tend to 1 when n tends to infinity. Therefore, the limit of the sequence n raised to the power of 1 over n is 1. So that is the way how you can prove the statements number 2 in theorem 5 using theorem 4. So the third statements in the theorems is this. The third theorem in the statements is that if x, sorry again, for those students who are attending the WebEx, if you are listening and attending the WebEx, could you please switch off your mic so that you won't disturb the lecture? Thank you for your cooperation. Please check your mic, okay? Please check your mic. Or if you are together with your friend, will you please tell your friends to also switch off the mic? Okay, so I'm looking at the item 10. So in item 10, you have an x, where x is a number that is remain fixed. So here n is any number. So I think in third item, x is any number that is larger than 1. So the third item in theorem 5, it says, if you have a number x, and you raise the number of x to 1 over n, then you take the limit of n goes to infinity. So this is a special type of sequence where the sequence does not only involve a entry of n, it also contains an n. For example, okay, an example of a sequence of 1 over n with x positive would be like the case where, say, I raise x as 2 and then 1 over n. Okay, so in this case, x is just a number which is 2 and it's positive. Then this will become 2 of 1. It will be a sequence of 2 of 1 over 2, 2 of 1 over 3, 2 of 1 over 4, etc. So the x to the power of n is a sequence where x is an constant. So if you have a constant of x which is positive, then the limit of x to the power of 1 over n is equals to 1. Again, you can try to prove this yourself by using theorem 4, where you map a function of f to this sequence. Okay, I think you can try to do this. I mentioned here, see if you can show some of them yourself. The fourth item is this. You have a power of x n, that is a number of x raised to the power of n, and in this case, x is a constant. So if x is a constant, what is the limit of the sequence x power n? So the answer is, if the magnitude of x is less than 1, then the limit of x power n is equals to 0 when n goes to infinity. Now this is the results in item 4 in theorem 5. Then you have also item 5 in the theorem 5, which says if you have 1 plus x over n sequence raised to the power of n. So this is another type of sequence which is very, very important as well. Here, x is any number. So x is a number that is real. So the limit of the secant x 1 plus x over n raised to the power of n, the limit of this when n goes to infinity is the natural number e raised to the power of x. Okay, so this is a very, very important result. You can try to prove it yourself, or maybe we will come back to this point later on. But anyway, e power of x is just the limit of the sequence 1 plus x over n raised to the power of n. Then the sixth of the item is that if you have a functions that, so if you have a sequence which is x power n over n factorial, the limit of this sequence when n goes to infinity is equals to 0 for all values of x that is real. Okay, so this is the result that is always real. So in other words, if you have any number that you think of, say for example 3.5, then 3.5 you can raise it to the power of n. So when n goes to very large, then 3.5 raised to the power of n, of course, will increase exponentially. But then in the downstairs, you have n factorial. N factorial is also a function that is also increasing. So when n increases, the 3.5 power n is a power function that is increasing very fast. Downstairs is also a function and factorial function which is also increasing very fast. But in the limit when n become very large, it turns out that this power, the factorial function is actually increasing much faster than the function upstairs, so that finally this one will wins and this one will lose out. And at the end of the day, this one will become larger and larger compared to the function of 3.5 power n. Then at the end of the story, this limit will just tend to 0. It is true no matter what values of x it is. It could be 3.5, it could be negative 3.5, or it could be anything. It could be, say, 10 to the power of log 100,000. Still, it would lose out finally when n's become infinity to the factorial function. So these are the results that will be recycled again and again in the later parts of this chapter when we study the limit of the series. So I have to spend a little bit of time to explain to you about theorem 5 because we're going to use these results again in the later part of the chapter. Okay, so these are the examples of the applications of the theorem 5. So if you are given all these kind of sequence and asked for the limit, then you can actually work out the limit of this sequence one by one by using the theorem 5 that is discussed here in conjunction with the rules of the limits in theorem 1. So you have to make use of theorem 1 and also theorem 5. Combining theorem 1 and theorem 5, you'll be able to work out the limit of all these sequence yourself easily. So I'm not going to go into detail of example 5, but I expect you to be able to figure out this yourself. Okay, so now I want to spend a little bit of time to explain about two definitions, which is a bit confusing to some of you. We are going to talk about two definitions and a theorem. The theorem is about the existence of a limit to an sequence. Okay, so this is a theorem that is very related to the sequence. So when we have a sequence, we always want to know whether a sequence has a limit or not. Right? So you want to know if a limit of the sequence exists. If the limit exists, then you want to know what is the values of that limit. Now, the theorem 6 provides a very powerful theorem that is a statement that is always true for all sequence. As long as the sequence is fulfilling this condition, then it will be able to tell you whether a sequence is having a limit or not. Or in other words, whether a sequence will converge or not could be easily understood by the theorem 6. But before we talk about theorem 6, the non-decreasing sequence theorem, we have to talk about two definitions. The first definition is the definitions of a non-decreasing sequence. So a non-decreasing sequence is a very simple idea That is, if you have a sequence written in this form, then the next term in the sequence is denoted by n plus 1, and the term before this n plus 1 term is a term of an, right? So it's like a plus 1 appears first in the sequence, then only the term a of n plus 1 will appear later. So generally, all the next term is denoted as n plus 1, and a1 is a term before the term of a plus 1. Now, if you have a sequence where the next terms in the sequence, if it's always equals or larger than the sequence before it, then this is called a non-decreasing sequence. That is, if you were to represent the sequence in an XY format, in the XY term, then you find that every term, every dot that represents the sequence will be either become flat on the to the right, or it will only increase. If it's not increasing, it must at least stay constant. Okay, so a non-decreasing sequence will not have a term that will become lesser. Okay, this would not happen. All the term in the sequence, or the next term in the sequence, will either equal to the term before it or larger than the term before it. For example, this is a very typical non-decreasing sequence. The next term in the sequence is always larger than the term before it. We also have this kind of sequence. This is also a sequence. N over n plus 1 is also a sequence that is non-decreasing because the first term is half. The second term is 2 over 3, which is always larger than a half. Then the next term to 2 over 3 is 3 over 4, which is slightly larger than 2 over 3. So the next term is 4 over 5, which is also larger than the term before it. So this is another example of non-decreasing sequence. Now, how about a sequence that contains a constant of 3, where all the terms in the sequence are all constants? This is also considered a non-decreasing sequence because it fulfills the condition of an less or equal to n plus 1. In this case, you don't have the smaller sign, but in this case, you have only a simple situations where the term before it is always equal to the term after it. So according to the definitions, a constant term is also a term that is fulfilling the condition of less or equals to. Okay, is less or equal to. Okay, so if the condition for less is not fulfilled, but the equal condition is fulfilled, therefore the statements that this next term is larger or equals to the term before it is still correct. Okay, so this is an example of a non-decreasing sequence. And then we have to understand there are two types of non-decreasing sequence. This is a very interesting subject, right? So if I give you a sequence, we should have a term 1 by 1, and it is told that this sequence is non-decreasing. So if this sequence is non-decreasing, what do you expect the values of the terms in the sequence? So you would thought that the terms will become larger and larger, right? So that is true because the terms in the next position will always be larger or equals to the terms before it. Therefore, there's only possible for the next term to be larger. It won't be able to become less than the term before it. So the next terms in the sequence is always increasing in the non-decreasing sequence. However, there are two situations. If you keep on adding the next terms, will the next terms shoot to the infinity? They are actually not quite the case, because if you add on term that is larger and larger, then it is possible that you could have two situations. One situation is the term will just get larger and larger, and then it will just go through the rooftop. It will just go to infinity. The another situation is the sequence, even though it's not it's non-decreasing, but it won't increase to infinity. It will keep on increasing, but finally it will not go through and rooftop. There will be some kind of bound that forms the boundary to the non-decreasing sequence. So for a non-decreasing sequence, even though the next term is larger than the term before it, but the term at an for any n will not be larger than the bound. We call this the bound. So there are two kinds of non-decreasing sequence. Consequence that is bounded or non-bounded. Those non-decreasing sequence that is not bounded will be just those sequence that will just keep on increase and goes to infinity. The other type of non-decreasing sequence is a sequence where it will keep on increase, but it will never go through a bound, where the bound is sort of like the upper limit of a bound of like a rooftop that is always higher than any terms in the non-decreasing sequence. I think this is an example. Let's look at an example of such a sequence. Okay, so we are looking at example of this. So this is obviously a non-decreasing sequence, and there's no upper bound. That means there's no bound where the values is less than it. Right? So we call this an upper bound. Upper bound is a number that fulfill this condition. So let us read the definition of the upper bound a little bit more carefully. So it says a sequence an is bounded from above if there exists a number m such that all the terms in the sequence is less or equals to m for all n. The number m is an upper bound for the sequence an. If m is an upper bound for an, but no numbers less than m is an upper bound for an, then m is called the least upper bound for an. Okay, so this is sometimes people find it a little bit confusing, but it doesn't need to be very confusing. What it says is that if you have a sequence like this, and you have many terms in the sequence, if there exists n values of m, such that an is always less or equals than m for all values of n. So that is a statement to say if there exists n values of m which is always larger than all the terms an in the sequence for all n, okay, all possible n, then m is known as the upper bound. If you look at the sequence of 1, 2, 3, up to n, this sequence has no upper bound because you cannot find any numbers of m which is larger than all the an terms in the sequence. Whatever m that you can specify, there's always an n where an is larger than m for this kind of sequence. Therefore, the sequence A, 1, 2, 3, 4, up to all the infinity, is a sequence that has no upper bound. However, this is a sequence that is non-decreasing. Now, how about this sequence? A sequence of n over n plus 1. So I have already explained to you, such a sequence is non-decreasing. Okay, so the next term is always larger than the term before it. So it is fair to say that the sequence an is a non-decreasing sequence because the next term an is always larger than the term before it. So if you make n to become larger and larger, would the an now goes to infinity? Answer is no, because the an is given by n over n plus 1. Therefore, it is not possible for an to become larger than 1. It's not possible because an is expressed as n over n plus 1. No matter what n is, no matter how large n is, n over n plus 1 must always be less than 1. Therefore, the sequence cannot be possibly larger than 1. So in this case, m equals to 1 is said to be the upper bound of the sequence of an. So that is the idea of the upper bound. M equals to 1 is an upper bound to this sequence. Now I ask you for another question if you understand the idea of upper bound. Is m equals to 2 an upper bound to the sequence? So the answer is yes. M equals to 2 is also an upper bound to the sequence because there's no an that is larger than 2 for all the n that is possible. Therefore, m equals to 2 is also upper bound. 1.5 is also upper bound. 1.3 is also upper bound. Any numbers of m that is larger or equals to 1 are the upper bounds of the sequence of an. But out of all these many values of the upper bound, m equals to 1 is the smallest of all the possible upper bound. So the smallest upper bound is known as the least upper bound. Okay, so you have to first understand that there exists a kind of thing called upper bound. Upper bound is always any number in which the sequence would never exceed. Right, so you could have many different values of upper bound. Out of all these possible values of upper bound, those upper bound, which is the smallest in value, is known as the least upper bound. Okay, so that is idea of a bounded, a upper bound of a sequence, and the definition of the least upper bound of the sequence. So you can look at this example, figure 11, illustrate the idea of upper bound. So if you have a sequence that is increasing or that is non-decreasing, for all the values of an in the sequence, it will never exceed m, it will never exceed l. Therefore, l and m are both the upper bounds of the sequence as shown in the figure 11.4. However, here illustrate that l is the smallest of all the possible upper bound. Therefore, y is the lowest possible upper bound. Then we think of L as the least upper bound in the sequence. Now, once you have understood what it means by a non-decreasing sequence and the upper bound of a sequence and the least upper bound of the sequence, then you can understand the theorem 6. The theorem 6 is applied to a sequence of non-decreasing, is applied to the non-decreasing sequence. It says a non-decreasing sequence of real numbers converges, meaning that it has a limit. When it says a real number non-decreasing sequence converges, it just simply means the real number sequence has a limit. So it says that sequence has a limit only if and only if it is bounded from above. Okay, so it just simply means if you have a non-decreasing sequence and you know that this is a non-decreasing sequence, and then it says the limit of the non-decreasing sequence exists only if the sequence an is bounded from above. Okay, so you said it, let me say it again. This theorem actually is divided into two sections. Okay, the first section is that you have a non-decreasing sequence, and if the sequence is bounded from above, then the sequence has a limit. The second part of the sequence is the opposite. If the sequence is bounded from above, then it has a limit. So that is what it means by if and only if. So I reread this sentence. It says a non-decreasing sequence of real number converges if it is bounded from above. A non-decreasing sequence of real number, if it's bounded from above, then it converges. Okay, so it just goes into two ways. A sequence is converges if bounded from above. If the sequence of an is bounded from above. The second part of that is that if a non-decreasing sequence an is bounded from above, then the non-decreasing sequence converges to a finite value. So when you combine both statements, it becomes if and only if. Okay, so that is the first part of the theorem 6. Then the second part of the theorem 6 says is, if a non-decreasing sequence converges because it is bounded from above, then the limit of the non-decreasing sequence is equals to the least upper bound. Okay, so that is what the theorem says. So a non-decreasing sequence, if it's bounded from above, then it must converge. When it converge, it must converge to the least upper bound of the sequence. So that is what I want to tell you about theorem 6. Now, any questions up to this point? Now we need the these few slides, theorem 6, and the definition of the upper bound, and the definition of non-decreasing sequence in the later part when we study series. Okay, any other questions from any one of you? Okay, fine. If there's no questions, then I cannot let you go at the moment. As a conclusions, before I close these sessions, is that we have so far discussed the theorems that tells us how to calculate the limit of an sequence, theorem 4 and theorem 3. Theorem 3 here and theorem 4 here. With these theorems, we will be able to calculate the limit of an sequence, and we have seen a few examples of using these theorems to solve some example. Then we also mentioned theorem 5, which is a list of very important result on the limit of some very typical but important sequences. Then we mentioned also the definitions of a non-decreasing sequence, the upper bound of a sequence and the least upper bound of the sequence, and explain that if a non-decreasing sequence is bounded, then it must converge. If it's converged, then it must be bounded from above. In addition to that, if a sequence converges to a limit, then the limit must be just equals to the least upper bound of the sequence. All the things that we have learned in the chapter of 11.1 is actually meant to be applied in infinite series. In order to discuss infinite series, we have to make use of the notions of the sequence before we can define series.